All right. Welcome everybody to Advanced Topics in Machine Learning, learning with conditional guarantees. But you're not seeing the slides on the screen. Welcome to Advanced Topics in Machine Learning. Hello. Cool. So there's a lot of you. So let me start off with like just an attempt to figure out who everybody is. So let's see. Raise your hand if you are registered for this course. Cool. Raise your hand if you are hoping to be registered for this course, but are unable because it is full or because of some other system problems. Okay, cool. Raise your hand if you are not hoping to be registered for this course, but just want to hang out here. Okay. Good. Let's see. How many of you would describe yourselves as PhD students? Okay. How many of you would describe yourselves as master's students? Okay. How many of you would describe yourselves as undergraduate students? Okay. How many of you would describe yourselves as third graders? Okay. Okay, that's Eli. And let's see. Okay, so that's like the age range. How about topics? How many of you think of yourselves as computer scientists? Okay. Statisticians. All right. Mathematicians. Okay. Economists. Anything I didn't mention? All right. Pretty good. Okay. So my ambition for today is, so first of all, just in case some of you are in the wrong place, typically, like for every day other than today, this is going to be like a math class. So I'm not going to use slides. We're just going to like write on the board. This is a theoretical class. Today, what I want to do, though, is sort of do the rah lecture where I suggest that this might be a fun class to take, go through some overview of the kinds of things we're going to cover and also sort of just basic parameters of the class. So today I'm using slides, but like, don't be fooled. It'll be a math class starting next time. Okay, so maybe like starting with some boring stuff. That's the organizational details. Okay, so I'm Aaron, and we have a TA, Natalie, over there. And if you haven't found it already, we've got a course website. So if you go here, then things you might find are like notes for the class. I'll try to have sort of pretty carefully typed up notes for everything we cover. Eventually there'll be things you need to turn in, like projects. We might have some organizational details, some topic ideas for projects there. And a link to join the Slack if you haven't already. Oh, and videos. So if everything goes well, there will be video recordings of the class that should be linked to from this website. You can either just remember the name of the website because it's got this catchy name, uncertaintyclass.com, or you can go to my website and there'll be a link from there. Okay, so if you're taking the class and you haven't already, you should sign up for Slack. It's linked to from the course website. I think I invited everyone who was registered for the class as of a few days ago to the Slack, but if you're not already in it, sign up for it. That's just how I'm going to communicate with the class. So, if project midterm report is due, I'll probably announce it there. If class is canceled or something, I'll announce it there. So that'll be a good place just to like ask questions and keep track of what's going on. And this will be a lecture-based class, so there's bi-weekly lectures. So Tuesday, Thursday, I guess you guys have figured out the time. this is sort of like a research class, right? We're trying to get everyone up to the research frontier on some interesting thing. This is going to be a lot more fun with active participation. I ask questions. I might say wrong things. You should point out when I say wrong things. This will be more fun if everyone's engaged. Right, and so like this is an advanced topics class. So many of you will have some familiarity with sort of the basics of machine learning, or even maybe the particulars of lots of areas of machine learning. The goal of this class is to bring everyone up to and beyond the research frontier of like some particular mathematical topic in learning theory, learning with conditional guarantees and various kinds of uncertainty quantification. And so it's going to be run in that spirit. So it's not going to be a class for which we have exams or a significant number of problem sets. Maybe we'll have a few just to sort of scare a few people away. But as a result, like like the main thing this course is offering is like the lectures. That's where we will be teaching and sort of appreciating the material. So attendance and participation is important. That'll be a good part of how grades are given out at the end. And the primary deliverable will be a semester-long course project. So basically, the ambition for this class is that you should produce a novel or publishable piece of research. Of course, it is not required that you discover something new and publish a paper. That's like the stretch goal, but that's what you should be trying to do when you set out to pick a project topic. The goal is to take something you've learned in this class, take maybe something you already know about, a domain area, some other mathematical area of computer science or statistics or learning theory, and use what you've learned here to do something new. Okay, that could be mathematical, you could prove a theorem, it could be empirical, you could sort of implement something and see how it works. But the goal is to write something that produces new knowledge and looks like a paper. Okay, so you're not going to fail you if you don't get the thing published, but that's the goal. And so you should approach this sort of main activity in the course accordingly. So it's research. So research is a team sport. It's more fun if you collaborate with people when you're doing research. You need to bounce ideas off of someone. So you're strongly encouraged to not try to do this on your own, but to form groups. Okay, so no hard and fast rules, but like I think a typical a good group size would be between 2 and 4 people. Okay. Try to find people who have common interests. The Slack can be useful for that. Maybe we'll make a Slack channel where people can sort of pitch research ideas and try to recruit the team. And so we'll have various check-ins. So maybe it'll take a few weeks just for everyone to get sort of acquainted with the kinds of things we're trying to do in this class. So after we learn a little bit, maybe I'll put on the website, some rough guidelines of project ideas, not that, even better if you come up with your own, but just sort of suggestions. And what you should plan to do is, and we'll probably have like a midterm check-in where, you tell us what you've done so far, give us a short write-up. But like the thing you should have your eye on, like by the end of the semester, you should have a write-up that kind of looks like a paper. Okay, so it should explain the problem you're trying to solve, whatever background knowledge needs to be known, what's already been done, and what you did. Okay, again, no hard and fast rules, but such a thing is probably at least 10 pages long. Of course, could be much longer if you need it to be. And you should also be ready to talk about it. So we'll take the last few classes. Most of the classes will be me lecturing to you, but the last few classes we'll set aside for project presentations where we will hear what you all have done. Okay. And so in the end, like the evaluation in this class will be based on the project and, like attendance and participation. Like it's probably not good if at the end I don't recognize you. Good. So that's going to be like the rough way this course is run and evaluated. Are there questions at this juncture? Okay. So, but yeah, so what are some of the kinds of things we're gonna think about in this class? What are questions we're gonna ask? And this is a non-exhaustive list. So we're gonna think a lot about probabilities and how we can make predictions that sort of look like real probabilities in various ways that will make precise. Even if, as we'll see, it's not possible to sort of really get our hands on true probabilities, if those are even sort of coherent concepts in various predictive settings. And the viewpoint we will take is that we want to make predictions that we can usefully use as if they were probabilities. Okay, and so like we'll try to do things like think about downstream of our predictions. What are we going to do with those predictions? And what like how do our predictions need to look like probabilities? What properties do they actually need to share with probabilities in order for the downstream use cases we have in mind to work? Like how do predictions need to look like real probabilities for them to be useful? We'll also think quite a bit about sort of uncertainty quantification. So in machine learning, we make predictions about things. If we're good at it, oftentimes we're right, but we're not always right. And so, especially if we're going to be using these predictions ultimately to take action, maybe even consequential action, it would be good to have some meaningful way to understand how certain or uncertain we are about particular predictions, not just like average statistics, like we get the answer right 90% of the time, but how certain are we that we got the answer right for this patient, right? If we're gonna make an incision or not as a function of the prediction, we want to have sort of meaningful uncertainty quantification about particular predictions. And so this is quite related to how we can estimate real probabilities, and this is something we'll spend a lot of time thinking about. The title of the course is Learning with Conditional Guarantees. And so unlike sort of most sort of error statistics that you see for machine learning models, things like error rates or false positive rates or false negative rates, or AUC, these are all metrics that in some sense average over all of the data. Okay, they tell us how performant the model is on a random example from, say, the training set. But oftentimes we are going to be interested in things that are not just random examples from the training set. We're going to be interested in particular subsets of the data. How sure are we that the thing in front of us is a pedestrian, not just like on average over all scenarios in the training set, but like conditional on our decision-making framework given the visual input, determining that we want to put on the brakes, right? Like how sure are we conditional on various events? And so we're going to think about sort of all of these questions, not just marginally, not just on average over all of the data, but we'll think about whether the kinds of guarantees we can give still hold when we zoom in on particular relevant subsets of the data. And what is relevant might depend a lot on what we're doing. Okay, so if we're thinking about if we're doing facial recognition and we're worried about fairness and bias, right? We might ask, what are error statistics of our methods, not just overall, but as broken down by race and by gender, despite the fact that an individual can have both a race and a gender. These are sort of criteria that can intersect, which makes the problem interesting. When we're thinking about using predictions for decision making, we might think about the error statistics of our prediction, not just overall, but conditional on our predictions inducing various decisions, and what the sort of downstream decision theoretic guarantees are, follow from that kind of thing. And we'll have a focus on trying to make predictions trustworthy in the following sense. Okay, like if for example, what we are doing is producing a probability distribution over labels, some distribution over outcomes. I'm 80% certain that the thing in the picture is a baby carriage, and 20% certain that it's a bicycle, and so I've used up all my percentages, but there's like an additional 1% somewhere that is a hot dog. Like if I have if this is embedded in some decision theoretic framework where there's actions I can take, I can slam on the brakes, I can eat it, then I might have a utility function that describes, like how much utility I would get, how happy I would be for each of the actions that I could take given what's actually in the image. Right? Maybe I'm pretty happy if I eat it and it's like a hot dog, but I'm less happy if it's a baby carriage. If I was given a true distribution over what the object was, I could approach this, in a decision theoretic way. I could say, what action should I take that would maximize my utility in expectation, given the distribution over outcomes that might be realized? Now, I'm not in general going to have true probabilities. It's not even clear that it's like a philosophically coherent thing to talk about the probability that something is a baby carriage versus a hot dog. Like, is that even a probabilistic predicate? Nevertheless, maybe we can make predictions so that one can safely treat them as if they are real probabilities in decision theoretic settings. Maybe the policy of taking the predictions and choosing the action that maximizes your expected utility under the necessarily, false presumption that the predicted probabilities really are probabilities. Like maybe we can arrange things so that that's actually a good policy. Maybe that's better than any other policy that you could use to map predictions to actions. And if we can arrange for things to have that flavor, then we'll think about that as sort of a trustworthiness guarantee, that you can trust the predictions and act accordingly and be guaranteed that that is the best thing you can do with them. Okay, so we sort of want our predictions to have this sort of ability for you to transparently treat them as if they are correct, even though we are in settings where necessarily it might not even make sense to talk about correct predictions. Okay, so this will be sort of something that underlies a lot of what we do. Okay, and finally, well, we'll do other stuff, so not finally, but among other things, a question we will ask throughout is, if we want guarantees, if we want guarantees on our predictions of the sort that maybe we talked about above, what do we need to assume about the data to be able to make promises about our predictions? Okay, like we could make very strong assumptions, as is typical in machine learning. We could assume that data is drawn IID from some distribution, and that we have the luxury of training on an independent sample drawn from the same distribution. That would be sort of the standard assumption in machine learning. But if you think about it, like that's a very strong assumption, right? Like in a lot of settings, like it doesn't even really make sense if you sort of zoom in on it to think about a distribution. Like, well, what is the underlying distribution? And even to the extent that there is a distribution, it might be changing. And so we'll be really interested in ways in which we can avoid making strong distributional assumptions. And one extreme end of that will be by assuming nothing at all about the data generating process. assuming that we're making sequential predictions in a setting where the data generating process might be completely arbitrary, might be governed by an adversary, whose only goal is to feed us data that will sort of ruin the kinds of guarantees that we're trying to prove. Okay, and we'll be quite happy when we're able to give guarantees in adversarial models like this, not because we necessarily always believe that sort of the world is adversarial, but that if we're able to get positive results while making minimal or almost no assumptions at all, that means that when we go and try to deploy our predictive technologies, we don't have to worry about our assumptions failing because we didn't make any. Okay, so the strength of sort of worst case analysis, the strength of being able to make guarantees even in sort of fully adversarial settings will be that we get extremely robust guarantees that are not reliant on assumptions that we might be sort of unable to guarantee or verify in deployment. Okay, so let's start thinking about probabilities, like different settings in which we might be able to speak of probabilities, starting with maybe sort of the easiest one. So suppose I asked you, what is the probability that if I flip a fair coin 16 times, I get exactly 9 heads? What are ways in which I could go about trying to answer this question? I'm not asking for you to do like a calculation in your head and give me a number. Just, like how might you go about answering this question if I asked it? Yes.
Flip a coin 16 times and count, like you can do it like 1,000 times and see.
Yeah, like we could just like try doing it, right? We could repeat this experiment. I could flip the coin 16 times and see if I get exactly 9 heads. If so, I'll like check it off on a list. If not, I'll write an X, and then I'll just do this a zillion times, and I'll count the fraction of the times I got 9 heads. Okay, that's one way I could approach the problem. How else could I do it?
Could think about all of the ways that you could flip a coin 60 times, all of the possible outcomes.
Yeah.
And then count the number of ways that have 9 heads.
Exactly. Like in this scenario, I don't even need to perform the experiment. Like I could pretty straightforwardly get like an analytic expression for what this is. Okay, so this is sort of like the idealized scenario for probability. We have, first of all, a mathematical model for the probability that I get heads if I flip a coin that abstracts away a lot of the messiness of the physical universe. I just say, okay, like I'm gonna flip a coin, the probability I get a heads is 1/2. So like that might not be like exactly true. It's like ignoring like exactly how I flip the coin, but it's like a good enough model. And we sort of have the model that each of these events are independent, and we've got a mathematical model for this. We can compute exactly in the mathematical model the probability for this event. And fortunately, in this setting, the mathematical model is a very close approximation to reality. And so the numbers we get are actually useful. If I don't want to do the math, I can just conduct the experiment repeatedly. This is a very easy experiment to conduct. Well, I might have to flip a lot of coins, but like in principle, it's an easy experiment to conduct. And like the beauty of it, of course, is that the answer I get from the mathematical model will, if I repeat the experiment enough, be very, very precisely confirmed by the experiment. Okay, so this is sort of like the ideal case for probability. Like this is kind of the thing you probably studied in Probability 101. Okay, suppose I ask, what is the probability that Kamala Harris wins the 2024 US presidential election? This is like another probabilistic question you can ask. In fact, if you go to Polymarket, like they'll try to give you like a number. As of a week ago when I made these slides, they thought Kamala Harris had a 52% chance of winning the election. So how should we make sense of this? Like, what do these probabilities mean? Yeah.
I think it could mean something like, if an individual person says it, the worst odds of a bet they would take.
Okay, so just like what they personally believe.
Yeah.
Okay, so you could sort of use this to describe like a degree of belief that you could put to the test by seeing whether they'd actually bet money at those odds. Yeah, okay. And that's kind of what polymarket is doing. I mean, people are buying and selling contracts that are essentially bets. But how could like the two people could take bets at very different odds? Like, how do I adjudicate between whether one of the probabilities is right and one of them is wrong? And does it even make sense to talk about probability in this setting? What do we think?
You could say, well, there's actually multiple elections that are happening like over time. So I could ask like, okay, if I look at all of them, I look at the ones that say 52%, is it actually 52% of the time that candidate won?
Yeah, or like it wouldn't be a way for me to judge like the quality of like a probabilistic estimate for this election, but at least if I had like a systematic way of making predictions across many elections, I could try to sort of judge the system somehow. I can see if it's consistently biased. Yeah.
It's your expected payoff given that you bet $1 on the event.
But how do I compute that expectation? Like, what is that expectation?
Over some probability measure falling from the sky.
Yeah, right. So like maybe like it is philosophically coherent that there is some probability measure in the sky. Like maybe in this setting, it's not at least, self-contradictory to say, okay, I think there's a 52% chance that Kamala Harris wins the election. Maybe you think that, there's really a probabilistic model of the universe, quantum physics is non-deterministic. If I somehow, rewound the universe and ran it over and over again from the starting point, over the stochasticity of whatever quantum effects are governing things at a particle level. Yeah, maybe you think it's sort of philosophically coherent to believe that Kamala Harris would win the election 52% of the time. But we would like, in order to like compute this, we really would need this probabilistic model to fall from the sky. This is sort of different from the question about the coin in sort of two ways. First of all, for the coin, we had like a very simple mathematical model that mapped very well onto reality. Here we don't. When you could try to take a political science course and maybe like try to write down some simple mathematical model in which you could compute probabilities, but like you wouldn't have much confidence that it mapped well onto reality. So we don't have any sort of analytic way of getting at these numbers. And similarly, like for the coin, you can just like repeat the experiment over and over again. But even though there are elections, presidential elections every 4 years, each of them are very different. Right, they have different candidates. They've got different issues. So this is not a repeatable event, right? Like you're not going to be able to get more than one sample from the 2024 election. So not only is there not like a mathematical model to sort of try to get at these probabilities, it's not something you can get at empirically either. You can't take the approach of repeating the experiment over and over and just counting the fraction of times Kamala Harris wins the election. It's something that's only going to happen once. Okay, does that make sense? Here's one more. Suppose I say, okay, ChatGPT told me that the leading cause of death globally in children under 5 years old is diarrheal diseases. What is the probability that this is correct? How should I think about this? It says maybe like even a little bit different than the election scenario. Anyone? But like, what are the difficulties in this question that maybe might bother you philosophically in ways that the question about the election didn't? Yeah.
I guess that the election hasn't happened, but this is either true or false. Like there's
Yeah. But like for the election, like maybe it was like hard to figure out what these probabilities were because we didn't have like a mathematical model and we couldn't repeat the event. But like at least in a probabilistic universe, it might have been like philosophically coherent to believe that there was a 52% chance that someone wins the election. Here, like this is either right or wrong, and it's not that it's like unknowable. I could go and do some research, like I could do a Google search, and I could figure out if it was right or wrong. Okay, the only problem is I don't know at the moment, but like it's not, like it's somehow like not philosophically coherent to believe that the probability is anything other than 100% or 0%, right? It doesn't like there's no randomness. There's no sort of randomness over which I can even express in a mathematically coherent way that there's a 52% chance that it is right. All of the coins have been flipped already. Like this is right or wrong. Okay. Nevertheless, like it might still be extremely useful to have confidence scores for language models, say, that express to us in probabilistic language the probability that something is correct or not, the probability that some claim is like a correct factual recall or a hallucination. And if we insist on those probabilities always being either 0% or 100%, we're going to be in big trouble, because the only way we can provide correct probabilities is by perfectly knowing the answer to every question, which we don't. That's exactly the problem we're trying to solve, right? And so here, like if we're going to think about giving confidence scores for LLMs in a way that we can treat probabilistically, we sort of need to grapple with like a maybe even deeper philosophical question. Like how do we, like what does it even mean to assign probabilities to things that cannot, things that are like inherently not probabilistic? Okay. And how can we do that in a way that is useful for downstream decision makers? So these are the kinds of things you're gonna want to think about. But do these examples make sense? Like, are there questions about, maybe like these increasingly troublesome uses of probability? Okay. And like it's not like I'm just trying to like think of some obscure gotcha to make you think probabilities are interesting. Like this is what we do all the time in machine learning, right? We try to produce probabilistic forecasts for quantities that are like basically fundamentally unknowable for the exact reasons we've just talked about. So for example, if I'm into weather forecasting, I'm going to frequently speak about things like the probability that it will rain tomorrow. If I'm into life insurance, I'm going to make my living trying to compute things like the probability that Alice will die in the next 12 months. If I'm in sort of criminal justice, I might try to predict the probability that Bob will be arrested for a violent crime 18 months after his release on parole. If I'm in predictive medicine, I might try to predict the probability that Carol will develop breast cancer before the age of 50, and so on, right? And these are all things kind of like the probability that Kamala Harris will win the election. These are not repeatable events, right? Like, of course, there's many days, but like whether it rains tomorrow is not an experiment I can repeat. We're never going to see a day that's exactly like tomorrow. There's many people that I'm insuring, but Alice has but one life to live. It's not like I can figure out the probability that Alice is going to die within the next 12 months, right? Like, maybe maybe this is sort of like something that in principle there could be some probability for if we live in a probabilistic universe, but we can't get at it. We can't have Alice repeat these 12 months over and over. And it could actually like maybe these things are less random than we think, right? Like maybe if we knew more physics and took more measurements, we would find that these things, maybe like macro events like this 12 months out are actually totally determined, right? So maybe this is actually like the LLM example where the probabilities really are either 0% or 100%. We just aren't smart enough to figure out what they are. Okay, so like all the time in machine learning, we're making predictions about things that are essentially not repeatable because we have a feature space that is sufficiently rich that we never see exactly the same example twice. Okay, and yet, like we need to make these predictions. We need to like figure out what we're trying to do here. Okay, and what's going on? Like, at some level, what we have is sort of a measurement problem. Suppose, we imagine that there's some distribution over feature label pairs. Okay, maybe, features X, maybe I'm a weatherman, and the features X are, all of the, measurements I get from weather balloons across the world, satellite pixels and satellite imagery and everything I'm measuring, some enormous feature space. And then there's a label Y, 0 or 1. Is it going to rain today or not? Okay. There's some distribution over these things, which is abstracting away, like maybe a lot of physics. And the thing that I purport to be predicting is the probability that it will rain tomorrow, given everything I know. Okay, so the probability under this distributional model of the world, which I don't know the details of, I can't compute these things analytically because it's complicated. Okay. The probability that Y is 1, the probability it'll rain tomorrow, not marginally, not just on average. I don't want to know just like the average propensity of rain in August or something. I want to know the probability it's going to rain tomorrow, like conditional on all of the measurements I've made today. Okay. Note, by the way, that writing down a model like this does not preclude a deterministic universe. It could be that in this model, once I have all of these measurements, if only I knew enough physics, if only I knew, the trick that God embedded in the world, that to figure out if it's going to rain tomorrow, you need to take, like the XOR of, the last 5 digits of some binary expansion of, something. If only I knew that, like the probabilities would be 0 or 1, right? So this model does not preclude that the world is deterministic. And the problem is, like the reason, even though this is what we're purporting to do, to predict the probability of rain given the features, the problem is like, if we have a rich feature space, right? Features include like the pixels and satellite imagery. We are never, no matter how long we are practically at weather forecasting, going to see exactly the same example, exactly the same X twice. And so unless we commit to some mathematical model of the world, some model that relates X's and Y's and for a complex setting like physical weather prediction, any model we write down would probably be unreliable. Unless we commit to some such thing, we just have no access at all to these conditional probabilities, because for every X, we have either 0 or 1 sample from the conditional label distribution given that X, right? So we've only seen a single outcome. Today is the only day that's ever occurred with this X. Okay, so we can't hope to learn or even like evaluate whether our predictions are correct for single examples. We can't measure individual probabilities. Essentially, the only thing we can measure are averages over sufficiently large sets. I can group together days by things that I think of as commonalities in their features. I can say, okay, I think that sort of barometric pressure is probably relevant to weather forecasting. So I'm going to like group together all of the days for which my barometric readings were in some range. And maybe I think cloud cover is also important. So I'll also say, okay, if the barometric pressure was, between A and B, and, the cloud cover was between C and D, I still have, 1,000 days on which I've made observations like that. I'm going to look at the average propensity of rain on that subset of 1,000 days. Right? Like that's basically what I can do. I can group together data in various ways, and I can measure averages over outcomes. And I can't group together the data too finely, because then I won't have enough examples sort of satisfying the conditions of my grouping, right? So the more data I have, the more precisely I can group the data while still being able to solve this measurement problem. But ultimately, I'm limited by my data. I'm not going to be able to measure the probability of outcomes conditional on the exact features I have. I need to aggregate them somehow. And like the problem that sort of we run into as forecasters is the aggregations that we can make, the measurements we choose to take, are necessarily much coarser than what we really want, these sort of true individual probabilities. Does that make sense? Yeah.
Could we potentially like calculate these individual probabilities exactly if it was a discrete distribution? So like we could observe individuals multiple times or
So if we had so like if we had sort of like a very impoverished feature space, if we said, look, I'm doing like weather forecasting, but like the only thing I know is the month. Okay, so like, yeah, then I can say, okay, I've seen like August a bunch of times. I've seen it almost 30 times, this month already. And I'll see August a bunch of times. Yeah, then I could like compute empirically the true probability of rain conditional on it being in August. Okay, and more generally, if the number of samples I have is substantially larger than the cardinality of my feature space, then I can expect perhaps to have seen each of the examples in that feature space many times. And then I can actually get at these true probabilities conditioned on everything available in the feature space. The difficulty, though, is that the cardinality of this feature space, even if everything is discrete, it's going to grow like exponentially in the number of features, right? So even if these are just binary features, right? Like even if the features are all, the answers to yes/no questions, as I accumulate D features, there will be 2 to the D possible feature vectors I could observe. And so like in order to be able to, like you're right that ultimately this is like a data limitation question. But the amount of data I would need to estimate quantities like this sort of grows exponentially in the number of features, even if the features are discrete. And in a typical setting, the feature space, therefore, will be much, much, much larger than the number of samples I have. Right? Like, even if you think about like this is like even if you think about the scenarios where we use the most data, training language models, where we have everything on the internet. Feature space there is sort of like all documents you could write. It's just vastly larger than the amount of data we have. Okay, so the typical case is that the amount of data we have is sort of much, much smaller than the cardinality of the feature space, and that's when we're limited to being able to make only sort of coarse measurements and not get at individual probabilities. Does that make sense? Yeah, good. Yeah, other questions, objections to this philosophical road I'm trying to lead us down? But it's true that this is ultimately like a data limitation. I mean, you could also complain, of course, at the other end that if all I was recording was month when trying to make my weather forecast, I still wasn't getting at individual probabilities. I had, done my coarsening at the feature collection stage, and that there's more stuff out there I just didn't gather. Okay. Yes, so like, how should we think about individual probabilities given our sort of fundamental inability to measure them? And maybe just to like put a slightly finer point on that, like our real like inability to get at individual probabilities. Like we are completely unable to distinguish a completely random world from a completely deterministic world. Okay, so let's say we've got some rich feature space of the sorts that we never can expect to see the same example twice. Okay, the outcomes are it rains or it doesn't. Here are 2 models of the world. One is a completely random world. It's that the features don't matter. Like, model 1 is you can ignore the features because what's going to happen behind the scenes, what God is really doing is yeah, he made up the features, all these barometric pressure readings just for fun, just to mess with you. Really what he's doing is he's just flipping a coin, and the probability that it rains is 1/2, conditional on the features. The true individual probabilities, conditional on X, really are 1/2. Or maybe what happened is the world is completely deterministic. It's just that, like, what you haven't learned yet what it is you should be looking at in the features to determine whether it's going to rain or not, right? Like maybe what you need to do is you need to very precisely measure the temperature at 1,000 degrees elevation. You need to like write it out in binary to 100 decimal points of precision, and you need to take the XOR of the 3rd, the 10th, and the 12th bit. And if you did that, you'd know whether it was going to rain tomorrow, right? And so maybe like on half of the days it rains and on half of the days it doesn't, but that's just because the temperature is randomized at that altitude. And actually, like, conditional on your readings, the probabilities are either 1 or 0. Okay. Either way, like this is going to be like observationally equivalent to you, right? Like either way, it'll look like for any subset of the data that I collect, it rains on half of the days. Okay, and yet, like, these two probabilistic models are sort of like maximally different if I look at total variation distance or something, right? Like in one of them, the individual probabilities are all 1/2. In the other, they're all either 0 or 1, which is as extreme as probabilities can get. Right, so like in some sense, these are maximally different probabilistic models, right? That if I look at the total variation distance between these two distributions, they're really, really far apart as you can get, and yet they're like observationally equivalent. Okay, so like, like even though we want to learn, we want to predict individual probabilities, the probability that it's going to rain tomorrow, the probability that Alice is going to die in the next 12 months. Like, we can't just set that out as our goal. Like that, like without making very strong assumptions about the world, right? Like you can go down that road. You can say, okay, I'm just going to assume that the outcome is like linear in all of these features. And under that assumption, I'm going to, solve a linear regression problem, and I'm going to assert that I'm computing individual probabilities. Well, that all hinges on this like false assumption that the world is linear. So unless you're going to make those strong assumptions, we really shouldn't set our sights on learning individual probabilities. Like this is sort of a simple example where even in two worlds where they are sort of maximally different, there's just nothing you can do to get them. So we need to think about different goal. Okay, any questions so far? Good. So let's talk about. Okay, so what are the kinds of things we could do? So we've resigned ourselves, maybe at this point, if you haven't objected to where I'm leading us, that maybe the universe is such that it supports real probabilities, and we're going to be predicting probabilities. Maybe there are probabilities that it's going to rain tomorrow. Maybe there are probabilities that Kamala Harris is going to win the election. And also, we're making predictions about those things, but we've sort of resigned ourselves that the predictions we're making are not necessarily going to be the same or even close point-wise to the real probabilities. We just don't have access to those, given sort of our access to the universe. And so what should we do? Well, one thing we could try to do is we could try to ask that our predictions pass various tests, satisfy various consistency properties that the real probabilities would pass, right? So we can't learn the real probabilities, but maybe we can at least falsify that the things we've predicted are real, right? Like we can rule out really bad predictions. And we can start with really simple consistency checks. And maybe as we start layering on consistency checks, we'll find that even though, of course, what we're predicting are not real probabilities, they are as good as real probabilities for tasks that we are interested in. And maybe just like foreshadowing a bit the kind of thing we'll try to do in this class, the things we want to do with those probabilities will sort of point us towards the consistency checks that we want our forecasts to pass. If there's something we could do with real probabilities that badly failed using our predictions, then the something we wanted to do would sort of be a consistency test that we could use to distinguish between real probabilities and our predictions. And maybe we could go back and ask that our predictions be consistent in the way that we needed for this downstream application. Okay, so let's think about calibration, which I'm going to think of as sort of like a level 0 consistency check, like the most basic thing we could ask for a set of probabilistic forecasts. And this, I'm going to call it level 0 because we're going to, over the course of this class, ask for more than that. We're going to layer things on top of it. Okay, so suppose I'm trying to like forecast the it's I'm flipping coins, and I'm trying to forecast the probability that the coin comes up heads. Okay, and maybe I've done some experiments. I've got a sequence that looks like this. Okay. What do you think is a good like estimate for the probability the coin comes up heads for this sequence?
By the very end. By the very end, you have like an equal number of heads and tails.
Yeah, it's like the same number of heads and tails. So maybe I should predict the coin comes up heads like half the time. That seems sensible. You know, right, like there, maybe by the way, I'm using a different coin every day, right? So like, there's certainly no way I could get at the individual probabilities. Like maybe what's happening is that, you know, whenever it's heads, I'm using a double-headed coin, and whenever it's tails, I'm using a double-tailed coin. But like from the sequence, it seems like heads and tails have the same propensity, so it seems reasonable to predict that the probability of heads every day is 1/2. Right? Like that at least appears on the surface. I can't say it's true. There's other ways this could have been generated, but at least on the surface, like it seems consistent with the data. Okay, how do I say that? Well, you know, let me look at the subset of days for which I predicted 1/2. In this case, that's all of them. I predicted 1/2 every day. And I compute the fraction of times it was heads, and in this case, it's 1/2. Okay, in this case, it was exactly 1/2, which is maybe like a little suspicious. But you know, if I did it for long enough, the fact that the propensity of heads was very close to 1/2 on the days when I predicted that the outcome would be heads with probability 1/2, that's a good sign. That's a consistency check. Like if I was really using a fair coin every day, that's a property that I would observe. If I didn't observe it, if I predicted 1/2 every day, but heads came up 3/4 of the time, and I had done this, you know, thousands of times, that would be very strong statistical evidence that my forecast was incorrect. Okay, so I can't say that these probabilities are correct because of this individual probability problem, but at least you know, like if they failed to satisfy a condition like this, I could say they're definitely not correct. Okay, so this is like a basic consistency condition. And this is what calibration is. What calibration is it says, okay, well, you know, like in this example, I predicted 1/2 every single day. I didn't have to do that, right? Like if I'm a weather forecaster, on some days I predict a 10% chance of rain. On some days I predict a 90% chance of rain. There's different predictions that I make. But if my predictions are calibrated, what that means is that if I zoom in on all of the days for which I made a particular prediction V, for all values of V, so all of the days for which I predicted a 10% chance of rain, it should be that the empirical frequency of the positive outcome should be what I predicted. On the days when I predicted a 10% chance of rain, the empirical frequency of rain should be about 10%. On the days when I predicted a 70% chance of rain, the empirical frequency of rain should be about 70%. Okay, that's calibration. it's a minimal consistency condition. If I somehow had a direct line to God and you actually knew the true individual probabilities of rain, then the predictions that I made would have this property. It's possible I can make predictions that have this property without knowing much about the true underlying process. In fact, we'll see in this class how to do it knowing absolutely nothing. But at least, like if I failed to pass that test, you would know for sure that my probabilities were bad. That's why I'm sort of calling this a level 0 consistency condition. Okay, does that make sense? I mean, over the course of this class, we'll formally define all of these things, but
We just want it to be like roughly B, right? Like there's only a single value for which it would be exactly B.
that's right. That's right. So like, in general, right, if I flip 1,000 coins, I don't expect exactly 500 heads. So typically, and when we get later in the class, when we define all of these things formally, we'll define them with error bounds. But yeah, you want it to be like roughly V, and there are sort of deviation bounds that sort of you would expect if you were predicting true probabilistic quantities. And basically what you want is that your forecasts should deviate from perfect calibration no more than like the real probabilities. Good. Yeah, other questions? Right, so just to remind everyone, like this is like, none of these are precise definitions. As we go on in the class, we'll be like dealing in precise definitions, but the goal here is just to like convey something at a hand wavy level. I just want to check if my hands have waved enough. Are there questions about this stuff?
There gonna be like a formal way in which this is like, is there like when you say level 0, like is there like a rigorous notion of the levels of consistency, or it's just?
Yeah, that's a good question. I sort of put level 0 on the slide without like a firm commitment to like what level 2 is going to be. We're going to add other conditions, but I think the answer to your question is no, or at least, I don't have a firm one in mind. There's not like I don't have in mind a single hierarchy of conditions that is canonical. Like depending on what you want to do, I'm going to talk about other conditions you can add on. But it's a good thing to keep in mind about what, it's a good question. Is there some canonical hierarchy of conditions that would let you complete this presentation and have a next slide that says like level 1 consistency? That'll be a good core project. Good. Other questions? Okay. How about this one? Does predicting 1/2 every day seem sensible here?
Stick of the nose against it.
Pick it up.
No,
No, why not?
because it's on odd days, it's with head.
Yeah. So like I could predict 1/2 every day, and I'd still be calibrated, so I would pass this level 0 consistency check. And yet, right, because there's still on half of the days, it's heads, on half of the days it's tails. And so if I look at the days for which I predict 1/2, which is all of them, and I look at the empirical frequency of heads, it is 1/2. Right, so I'm calibrated. I'm just as calibrated as I was on the last slide, right? In both sequences, I was like perfectly calibrated. But somehow like 1/2 seemed like a reasonable forecast here. Uniformly predicting 1/2 no longer seems reasonable here, despite the fact that I'm calibrated. And it's because like I'm making this uniform prediction, but like evidently there's this like alternating sequence, heads, tails, heads, tails, heads, tails, right? And my forecasts haven't picked up on that, and this structure has not caused my now like clearly bad forecasts to violate the calibration condition. right? So how come? Well, there's various ways you could think about explaining why a forecast of 1/2 is not reasonable. But one simple one, sticking to calibration, is to notice that although I am calibrated on the whole sequence, if I look at the subsequence of even periods and I look at the subsequence of odd periods, on those subsequences, I'm no longer calibrated. Right? Like if I was producing correct probabilistic forecasts, if I had really gotten to these individual probabilities, then not only would I be calibrated on the whole sequence, but like I could take any subsequence of days fixed up front, things like odd days or even days, and I'd still be calibrated, right? Because the outcomes would be flipped only after I selected out this sequence. But here, if I look at like the odd days, I'm really badly calibrated. I predict a 1/2 chance of rain on each of these days, and yet on the odd days, it rains 100% of the time. Right, like that's sort of like a maximal calibration violation. Similarly, on the even days, I predict a 1/2 chance of rain, and yet it rains 0% of the time. Okay, so even though I'm calibrated marginally on the whole subsequence, calibration fails like catastrophically on various subsequences. And so one thing you can ask for, and we'll think about this a lot in this class, called multicalibration, is I could ask that my forecasts be calibrated not just overall, but on a bunch of different subsequences. And this will be most interesting when we think of subsequences that are not necessarily disjoint, that are intersecting and can depend on feature space in interesting ways. Okay, so but like this is in some sense how multi-calibration will be, you know, a couple of levels up from level 0 calibration. We're asking not just for a single marginal calibration guarantee, but calibration on a bunch of overlapping subsequences. Okay, now calibration, it's all about predicting averages, means, like the probability it's going to rain today. But if I've got a real valued label space, the expectation of a random variable, the expectation of the label, isn't the only statistic of the distribution I might be interested in, right? Like real valued random variables have other distributional properties. I could be worried about their variance. I could be worried about their quantiles. And just as we can think about calibration and higher level guarantees like multi-calibration for means, we can think about these for other distributional properties too, for quantiles, for variances. And so quantiles turn out to be pretty useful for uncertainty quantification. We'll talk about conformal prediction in a moment. Yeah, and sort of a general philosophy we'll sort of try to chase down in this course is that if we make predictions that are indistinguishable from real probabilities, not in every possible way, but with respect to a certain class of tests, okay, you can think of these multi-calibration constraints, calibration on different subsequences, as just a collection of tests aimed at falsifying the fact that our probabilities are correct. Then they will be as good as real probabilities for any application that interacts with them only through tests from that class. Okay, like depending what you're doing, you're not going to be making decisions in entirely arbitrary ways using our predictions. You're going to be doing so in structured ways. Maybe you're going to be solving some optimization problem. And if what you're doing with them only requires that the probabilities be consistent with respect to some class of tests, then if I can guarantee that my forecasts are consistent with that class of tests, even if I can't promise they're real individual probabilities, they will be good for that task. And this is sort of a thread that we'll pull on quite a bit in this class. Okay. Let me tell you a little bit about one application we'll see a bit of for sort of multi-calibration of quantiles. And this is a popular way of quantifying the uncertainty of predictions using prediction sets. We've got a bunch of black box methods now that are pretty good at making predictions. This is the topic of most machine learning courses. And so, sometimes when we're gonna, make high stakes decisions as a function of what's been predicted, we want to know like which particular predictions we should feel confident. And so one way to try to express the uncertainty of predictions, if we're predicting labels, say in like a discrete setting, like maybe I want to identify what's in an image, is that rather than trying to just make a point prediction, rather than always just coming up with a single label, if I'm uncertain about what's in the image, I might want to produce a set of labels, okay, that specifies where my uncertainty is. I still prefer a single label if I'm really sure. Maybe I, feel quite confident this is a fox squirrel, and I can just say like fox squirrel. But there might be other scenarios where I don't exactly know what's in the image, but I know it's not stop sign. I know it's not a 60 miles per hour sign. One way of expressing where my uncertainty lies is by saying, look, there's a set of things I think it might be. I think it might be a marmot. I think it might be a fox squirrel, a mink, a weasel, a beaver, a polecat, but I don't think it's a boat. Okay. This is some way of expressing not just like quantitatively how uncertain I am by how big the prediction set is, but like where my uncertainty lies. And it might be that for whatever downstream task I have in mind, I actually don't care about the species of critter that's in front of me. Maybe I'm just trying not to hit it. And like all of these lead to the same action, which is apply the brakes. Okay, so there's one way to do it. Prediction sets make sense even when, like in a regression setting, if I'm predicting a real valued outcome, in which case the set is often just an interval. Like, if the label's real valued, if I'm predicting like the number of inches of rain, I don't have to commit to like a single number. I could say, oh, well, I think, there's a 90% chance that we are going to receive somewhere between 1 and 1.5 inches of rain tomorrow. And the goal here, these prediction sets should have some meaning. The goal is that they should contain the true label with some target probability. Like they should contain the true label 95% of the time. Okay. And then the question is, like, since I've walked down the garden road of individual probabilities, like what does that mean? Like 95% of the time over like what randomness? And so to give you a sense of how you might approach this problem, and then like the kinds of things that might still be desired, let me give you like a 1.5-minute crash course in conformal prediction. We'll devote several lectures to this later on, so don't worry if it goes by a little fast, but here's conformal prediction, split conformal prediction. So in conformal prediction, you take some arbitrary model for making predictions. For illustrative purposes, let's say it's a regression model. The labels are real valued. So you've trained, some model, logistic regression model, random forest, neural network, doesn't matter what it is. The point is it's an object, it takes as input features and it outputs a number, makes a point prediction. And then, you think really hard and you come up with something that you call a non-conformity score. Again, it could be anything, but your intention is that it should express how surprising it would be if the label, how surprising it would be to your model if the features were X and the label was Y. Okay, so it's just some function, takes as input features and labels and outputs a real number. Think about higher numbers corresponding to like larger intuitive, measures of surprise. Okay, but like we're not going to assume anything mathematically about this function. It could really be anything. The maybe simplest version you could take if you had a regression model is just, given features X and a potential outcome Y hat, maybe your surprise is just like the absolute value difference between f of X, what your model thinks the label is going to be, and Y hat, what the label actually is. So you're more surprised if the label is further away from your prediction. Okay, and then what do? Well, if you're in one of these nice settings where maybe we're going to assume the data is drawn IID, and I've got a holdout set that consists of IID examples drawn from this distribution. One thing I can do is I can compute this nonconformity score for each of the labeled examples in my holdout set. Okay, each of them gives me a number. So now I've got some empirical distribution on these numbers, this empirical distribution on how surprised I was by the real label, given what my model predicted. Okay. And I could just compute some 95th percentile quantile of that empirical distribution. I could find a threshold such that 95% of the time, my surprise value was below that threshold. Okay. And then what does conformal prediction have us do? Well, on a new example, I'm going to produce the following prediction set. On a new example X, I know what my model predicts, f of X. And I will include in my prediction set all of the labels that would generate surprise value, that would generate nonconformity score less than this threshold, which remember was the 95th percentile quantile of the empirical nonconformity score distribution on the holdout set. Okay. So in this simple example, this would just be a prediction interval of with tau around the point prediction of my model. Okay. And it's not too hard to convince yourself, we'll work this out in class, it's pretty straightforward, that if indeed your new example is drawn from the same distribution that your holdout set was, then the probability that the prediction set contains the label on this new example is 95%. How come? Well, because this was a 95th percentile quantile of the nonconformity score, and the fact that the new example was drawn from the same distribution as the holdout set means that the probability this new example is more surprising than 95% of the examples you've seen is only 5%. Yeah.
But is this when the holdout set grows bigger and bigger?
When what?
So when in the limit case, when the holdout set grows bigger and bigger.
So there's an error term here that I'm abstracting away for now. Yeah, so it won't be exactly 95%, but so if I had the 95th percentile quantile of the true underlying distribution, this would be the statement. There will be some deviation bound given that I have a holdout set that will shrink with the size of it. And we'll go into detail when we actually teach this, but yes, good point. Okay, does this make sense? Okay. Okay, but this is a marginal guarantee, right? It doesn't promise that, like on this example, I cover the label 95% of times. It promises that for 95% of examples, I cover the label. Okay, those are not the same thing. And so just to maybe like put a finer point on that, why might we be unhappy with marginal guarantees? Well, suppose we've got a patient who's gone to the emergency room. Maybe it's like early in the COVID pandemic, and we're trying to ration ER beds. And maybe the doctor says, okay, given your features X, our model predicts that your blood oxygen level in 24 hours time is going to be F of X. Maybe as a result of that, we're not going to admit you. And the patient says, how sure are you? And maybe the doctor just like read up on conformal prediction and says, oh, well, I've got a 95% prediction interval that your blood oxygen level will be in this range between some lower bound and some upper bound. And, like none of those are sufficiently dangerous to admit you, so we won't. And our patient, wonders, what does this mean for me? And like ideally, like what the patient would want if she was going to try to take, like her utility maximizing action given this forecast, is that she would hope that like the forecast was an individual probability about her, but conditional on everything that was known about this patient. Somehow, maybe with the randomness is over the unrealized or unmeasured randomness of the universe, that there was a 95% chance for her as an individual that her label was going to fall within this range. This is what she needs for decision making. What conformal prediction and calibration and other marginal kinds of guarantees will give you, this will be marginal coverage. It'll say, something that, you know, syntactically looks a little bit similar when you write it down in math, but semantically is quite different. Now the probability is not conditioning on X, but is over the randomness of X. It's saying for 95% of patients, our prediction intervals cover that patient's label. And so, for example, if our patient worries that perhaps she's part of a medically relevant demographic group that makes up less than 5% of the population, it is entirely consistent with the guarantees of a marginal prediction interval that it is wrong, it fails to cover the label 100% of the time for people in this group, right? Like marginal prediction intervals, which only promise something for 95% of people, for 95% of examples, might have the property that they just fail to learn some relevant structure of the distribution on a subset of the data distribution that makes up less than 5%, and paper over that failure to learn with, you know, over coverage on some other 5% of the data. Okay, that's entirely consistent. Now, if we knew what these groups were ahead of time and they happen to be disjoint, these medically relevant groups, you know, maybe we could just calibrate or run conformal prediction methods separately on each group. But oftentimes medically relevant demographic groups aren't disjoint. Right? So suppose our patient asks the doctor, what about for people like me? Well, remember, you know, we don't have data to measure individual probabilities conditional on all of the features of an individual in a high dimensional space. And so to ask the, to think about this question, what about for people like me? You have to decide what like me means. There's different ways of grouping patients together so that you have enough data to estimate probabilities. So there's different ways the doctor could respond. Say, well, for African Americans under the age of 50, the 95% prediction intervals from A to B. And for women with a family history of diabetes, the 95% prediction intervals from C to D. And for people with egg allergies and no history of smoking, the 95% prediction intervals from E to F. And our patient could be a member of all of these groups, right? Like all of these could be people like her. These are not mutually exclusive. And all of these intervals could be different. In fact, consistent with like the promise of a marginal prediction interval is that like A to B could be like a disjoint interval from E to F. So like, what does this even mean? Like, how's she supposed to use this information? Okay, this is the kind of thing that could come up with conformal prediction. And this is sort of like this problem we talked about with coin flipping, where maybe we're calibrated overall, but like when we look at the odd days or we look at the even days, we witness a failure of calibration. Okay, well, maybe we cover 95% of examples overall, but when we look at women with a family history of diabetes, we don't. And so one thing we're gonna learn how to do, this is basically going to be multi-calibration, not of means, but of quantiles, is to give prediction sets that have group conditional coverage guarantees. I might have groups that are overlapping. Maybe they're defined by shape and color or luminosity. Or maybe they're these groups, right? They're just arbitrary groups defined by the feature space that don't have to be mutually exclusive. Okay. What I might want, something stronger than this marginal coverage guarantee, is that I should be able to give prediction sets for every example, not multiple prediction sets, not 10 different prediction sets if you're a member of 10 different groups, but a single prediction set for each patient, such that these prediction sets are, of course, we can't get at the real individual probabilities. We can't give individual fully conditional predictions, but I want these prediction sets to be correct, to satisfy a basic consistency condition, conditional on membership in each of these demographic groups. Okay, so I want that for each of these demographic groups, when I zoom in on those groups, I get 95% coverage. So it should be when I zoom it, I give a single prediction interval for every person. When I zoom in on those people with egg allergies and no history of smoking, I cover 95% of the labels. When I zoom in on women with a family history of diabetes, I cover 95% of the labels. When I zoom in on African Americans under the age of 50, I cover 95% of the labels. Okay, all of these consistency conditions should be simultaneously satisfied for the single set of prediction intervals that I produce. Okay, so that's one of the kinds of things we're going to try to do in this class. I mentioned we're also going to try to relax distributional assumptions whenever possible. So in this sort of quick whirlwind description of conformal prediction, it was kind of important that the data was IID, or at least exchangeable, and that I had a holdout set drawn from the right distribution. And so in machine learning, this IID assumption, or this exchangeability assumption, is extremely convenient. It essentially says that the future has to look like the past, but it's often not true. It's often not it's often not consistent with the world. So just to ruin a joke, yeah, here we've got a mall Santa. We've got this young man. Maybe he's about to enroll in Penn, and he's just made it to the front of the line, and you can tell from his face that he's pretty disappointed. This isn't the gift that he wanted to get. And it's because Santa is holding like this Barney doll and says, well, this year we pre-made your gift based on data-driven insights from your wish history. And the joke is that the sequence of wishes you make to Santa Claus over the first 18 years of your life is not an exchangeable sequence. So we're going to try to, thank you. We're going to try to deal with this. Okay, so we're going to try to figure out how many of these guarantees we can recover by making no assumptions at all on the data. We'll assume that data arrives sequentially and selected by an adversary. And it's going to turn out that we can do quite a lot, even in this very difficult setting. And this will turn out to have very close connections with game theory, and in particular, the minimax theorem. Like when trying to learn against an adversary, you're really playing a zero-sum game. And so figuring out how well you can learn is closely related to analyzing the value of that game. Okay, so in the last 4 minutes, just sort of a rough roadmap of topics that we're going to cover. This will possibly change as we go along. We're going to start at the very bottom. We're going to think about this a little bit as building up a hierarchy of consistency conditions. And we'll start at the very bottom of this hierarchy and just think about marginal guarantees. How can we make predictions that don't have statistical bias, that are consistent marginally with the mean? And what we'll see is that if we have some method of making predictions that does have non-zero statistical bias, then by correcting that statistical bias, we actually make our model more accurate. We decrease squared error. And if we're predicting quantiles, we can try to have our quantiles be correct marginally. And if they're not, and we correct it, we'll improve another loss function called pinball loss. And more generally, we'll be able to do this for any statistic of a distribution that is what's called an M estimator. It can be elicited by solving some regression problem, minimizing some loss function. Squared error elicits means, pinball loss elicits quantiles, and other distributional properties are elicited by other loss functions. Some distributional properties cannot be elicited. And these marginal guarantees are quite weak, but as we'll see, as we already saw a little bit, marginal quantile is already useful for conformal prediction. And then we're going to try to layer on more demanding guarantees. So we'll talk about calibration. Calibration, as it's typically spoke of, is sort of for means. We want our models to be statistically unbiased, conditional on their own predictions. We can do the same thing for quantiles and more generally other M estimators. And it's probably useful to pause at this point in the class and ask, like, who cares? Like, why are we talking about calibration other than it being sort of aesthetically nice that our predictions are consistent in this way with real probabilities? And we'll think about this through a decision theoretic lens. we'll try to interpret calibration as a trustworthiness guarantee. It'll turn out that, in a certain sense, if you need to take an action and all you know are the forecasts I've made about the future, if my forecasts are calibrated, then there's a formal sense in which the best thing you can do is to trust that my predictions are correct and optimize accordingly. Okay. Then we'll start layering in more conditioning events. We'll talk about multi-calibration, mean calibration conditional on membership in groups. This will sort of look like gradient descent on squared laws. We'll think about quantile multi-calibration, quantile consistency on multiple groups. This will look like gradient descent on pinball laws. And we'll think about calibration, multi-calibration on groups defined by downstream decision-making functions, which will give us strong decision theoretic guarantees like swap regret. Then we'll have an interlude in which we talk about zero-sum games and the minimax theorem. And the reason we're going to do this is because this will give us a toolkit to give strong conditional guarantees, both calibration and learning theoretic guarantees in adversarial settings, where we don't need to assume anything about the data generating process. Okay, we'll get existential proofs and we'll derive efficient algorithms as well. And we'll see some applications. We'll think about how to make predictions if we don't know ahead of time what loss function we're going to care about. We want to do well for all of them simultaneously. We'll think about how to give accuracy guarantees, even if we don't know what the distribution is going to look like in the future, if the distribution might shift. We'll think about using these tools for ensembling and the connection to Oman's agreement theorem. And we'll interpret some of what we're doing as boosting algorithms, not for classification error, but for squared error regression. All right. So that's the broad overview of the class. Starting next class, we'll actually start doing some of this stuff. But in the last minute, are there any questions? All right, and I'll see some of you guys on Thursday.
Oh, yeah. Oh, this is all after.
Carry on. What do I hire a TA
I
for?
forgot what you allowed.
Yeah, it's a good question. I don't know if it's great.
I just did.
I don't know how many are.
Yeah. You got it like today.
If you send me an email.
Like, it goes on, you'll get it.
Yeah.
One, I should go.
Okay.
Yeah, that haven't already.
Yeah.
Not. For me, I give it a whole- for you, it's a bit- Well, I thought Aaron. Oh, 51.